Hello Sprouting into STEM students, I'm Beatrice and today we're going to be talking chemistry. So I'd like to start, before we get into our experiment, we need to cover some basic chemical principles, and I'd like to start with talking about atoms. Atoms build molecules, and molecules build our entire universe. Every atom is formed by joining protons, neutrons, and electrons. For example, hydrogen, the atom hydrogen, has one neutron, one proton, and one electron. However, helium, another atom, has two protons, two neutrons, and two electrons. The number of protons and neutrons determines what atom is which. So, when atoms interact, the electrons are the one making the friendships. So if you think that for atoms to form molecules, they need to make friendship, and in my example, the electrons are the ice cream. Bear with me. So these friendships that I'm talking about between the atoms are actually called bonds. And today I'm going to be talking about two different types of bonds, ionic and covalent. So bear with me. In ionic friendships, there is one mean and strong person, and the ice cream, in this case, which is the electrons, so the big strong person takes all of the ice cream, and they're not equals and they don't share. This is the same case as in an ionic bond. Chlorine is much stronger than sodium, so it ends up taking all the electrons for himself, and by doing that, it forms a bond. However, in covalent friendships, the two people are equal and they share the ice cream equally. And that's the same thing that happens in covalent bonds. The hydrogen and the hydrogen and the oxygen share the electrons equally and they're able to form water. So this molecule right here, H2O, is also known as water. And this molecule right here, NaCl, is also known as table salt. So, our experiment today explores covalent bonds and what happens when covalent bonds don't act exactly like they're supposed to. So, covalent bonds, theoretically, and in the perfect scientific world, share all their electrons equally. However, in most cases, that's not true. And what ends up happening is that bonds create polarity. And polarity is when electrons are shared unequally between covalent bonds, which kind of goes astray from everything that covalent bonds are supposed to be, but in the world of chemistry, there's always a ton of exceptions, and you either learn to love it or you learn to hate it. The easiest way I can explain bond polarity is to show you with a diagram. So this is a water molecule, right? H2O. And this molecule you might not have seen before. It's called methane. I want to show you guys what's the difference between a polar molecule and a non-polar molecule. Even though both of them have covalent bonds. This bond is covalent, this bond is covalent, all of these are covalent. The electrons in those bonds are shared equally or unequally. So here, I'm going to show you. In a non-polar molecule, even though the hydrogen and the carbon have a difference in strength, the carbon is much stronger than the hydrogen. Because all of the arrows that I drew are facing each other, they cancel out. And since they cancel out, there isn't a difference in strength from one side of the molecule to the other. All of the ends cancel out, they're equal. However, if you pay attention to the molecule up top, the water molecule, the arrows don't cancel out. So, since this arrow is pointing this way and this arrow is pointing this way, the oxygen molecule is much stronger than the hydrogen. Because it's much stronger, it's able to pull most of the electrons towards itself. And so they're still sharing, but they're not sharing equally. And that's what makes the molecule polar instead of non-polar. And so, although these two molecules are still covalent and they're still sharing their electrons, the oxygen is stronger than the hydrogen, and so it's able to pull more. However, the carbon and the hydrogen, because they're in a molecule of this shape, and all of the arrows cancel out, they all share equally. One huge concept to get from this lesson is that like dissolves like. What happens when you put oil in water? Do they mix together? They don't. Why? The only explanation is polarity. The oil is nonpolar, and water is polar. They don't mix together because the bonds can't interact with each other. And so that's where this saying comes from. Like dissolves like. Polar bonds like to react with polar bonds, and nonpolar bonds like to react with nonpolar bonds. Our experiment today is called paper chromatography, and it's a technique that's used to separate mixtures using the difference in bond polarity.
Paper chromatography works as follows. Fill each container with oil, water, and alcohol. Grab filter paper and cut it into strips. Draw a line and pencil through the bottom of each filter paper. Label S, the dot with Sharpie, which has nonpolar ink, and label W, the dot with washable marker, which has polar ink. As the solvent, which is the liquid at the bottom of each cup, moves up the filter paper, depending on the polarity of each component of the ink, it'll separate the ink into phases. Each color pigment has a certain polarity different from each other, and this is why chromatography works. Because each pigment has a different polarity, it allows a mixture to separate and show all of its components. For example, in the water beaker, the marker ink rises higher, proving that it is polar because water is polar. This also proves that the Sharpie ink is nonpolar because it cannot interact with the water. As each solvent rises through the filter paper, it drags up the ink that follows with its polarity because, like we've listened to before, like dissolves like, and so similar things will interact together and go up the filter paper. The vegetable oil is nonpolar, so doesn't move the Sharpie ink or the washable marker. So we can assume that because the vegetable oil has a different polarity, it's less nonpolar than the Sharpie marker, it's not enough to pull the Sharpie ink apart. Now, if we examine the water container, water is extremely polar. Therefore, it's able to move the polar washable marker, but not the Sharpie, which is nonpolar. Also, since the filter paper has a very polar bonds in between the paper, you can see that the washable marker also moves up the filter paper more because it's more attracted to the paper and the water. Now, we can observe that the rubbing alcohol is 70% alcohol and 30% diluted with water. Therefore, it's able to move both the Sharpie and the marker. But if we think about it, the paper is polar. So even though the Sharpie ink is very attracted to the alcohol solvent, the marker is also very attracted to the polar filter paper. And that's why both the washable marker and the Sharpie can move to the same level that they reached in the last scenario with the rubbing alcohol, because the Sharpie is attracted to the solvent, which is the rubbing alcohol, and the washable marker is very much attracted to the paper. So both of them can be separated. And if we look at it, the Sharpie is separated into blue and purple pigments, and the washable marker is separated into green and red pigments. And scientists will do with this information is they will do an analysis of color. So for example, in the middle strip, we can tell that the green pigment in the washable marker is more polar than the red pigment because it travels further up the paper. And so this is a couple of things that scientists might think or look at while they're doing paper chromatography. This concludes our lesson today. I hope you guys enjoyed it, and have a nice day.